Okay, welcome to the class, and we are going to learn something very interesting. So, about blind decoding, okay, and of course it is coupled with the Coreset design, and we'll see how it happens, okay. So, this is what we have been discussing, and we will continue discussing that in today's classes, okay. Just a recap of the Coreset, okay. It can span how many symbols? 1, 2 or 3 contiguous symbols. Okay, just an example, 1 symbol Coreset, 2 symbol Coreset, okay, and so that's an example, and it can come anywhere in the slot, okay. This figure, what is this showing? Okay, so this is 1 symbol Coreset, and we looked at the hierarchy of how it is constructed, starting from resource element to this resource element group, and then CC, right, and then the aggregation level, okay. We saw that, and basically, so one REG has how many, REG is equal to 1 PRP, right, okay, and 1 CC is equal to 6 REGs, okay, correct. And if it is basically, we are defining for 2 symbols, so what happens, REG is within a Coreset are numbered in increasing order in a time first manner like this, okay, if it is for 2 symbols. So, REG 0, and you will have to allocate REG 1 to the next symbol. Similarly, if it is there is third symbol REG 0, 1, 2, that is what is going to happen, okay. So, that is what is said here, starts with 0 for the first OFDM symbol and the lowest number resource block in the Coreset, okay. If this is where in the frequency it is beginning, okay, right. So, this is the frequency, okay. So, it will begin REG 0 from begin from here, and then you move on to the next symbol and go on like this. Okay, so for 2 symbols, this is 1 CCE, okay, control channel element. And then we looked at Coreset in slightly more detail, and what we said here was the Coreset is basically allocated symbol OFDM symbol 0 and 7, and the duration is 3 symbols, correct, okay. 3 OFDM and Coreset duration is 3 OFDM symbol, that is what is shown here. And it comes in slot 0 and 1 with a periodicity of 5 slots, okay. So, 2 slots followed by 3 slots of no Coreset transmission, and it goes on like this, okay, right. So, this is where we stopped, and we will continue our discussion from here, okay. Now, what is happening here is, okay, so I am taking another Coreset example, okay, and see how it is allocated and how UE will search using this Coreset. Okay. So, what are we saying here? Okay. That first thing I am showing you here is that the Coreset is basically defined at an aggregation level of 4, okay, right. So, 4 CCEs are clubbed together, correct, and then only a user DCI will be mapped onto it, okay, correct. So, that is what this aggregation level 4 means, okay. And we calculated how many G, what will be the size of G if it is aggregation level 1, 2, 4 and 8, okay, correct. So, this is, so for this user, the Coreset is defined only at aggregation level of 4, okay, and allocated OFDM symbols are 0, 4 and 8 shown over here, 0, 4 and 8, okay, right. And so, aggregation level 4 means that this is 1 CC, this is second CC, this is third CC, and this is fourth CC. Okay, so the user data will be mapped, or the user DCI will be mapped onto one of these Coresets. Okay, right. So basically, this is Coreset, and a user's data will be mapped onto one of these locations. Okay, so what am I saying here is map. So user is allocated aggregation level of only 4. So this complete location will be used for the user because aggregation level is 4, okay. It cannot, so G is defined accordingly, right. So, you have the complete chain, PDCCH chain, okay, gives a certain number of QAM symbols, and those QAM symbols all will be mapped onto this location in the Coreset. I am not saying this, one of these locations, okay. So, what will happen here is, okay, so this is how the Coreset is defined, okay, allocated OFDM symbol is 0, 4 and 8, okay, right. Duration is 1 symbol, you see this only, it is defined over 1 symbol, correct. So, allocated symbols are 0, 4 and 8, and so it will begin at 0 and at 1, 4, Okay, so this is the 4th symbol and this is the 8th symbol, that's all. Okay. Period is 1 slot, so it will repeat after 1 slot. Okay, so I have shown you this is 1 slot and it will repeat after every slot. That's the period. Okay, in the last slide I showed a period of 5 slots. Okay, here it will repeat after every slot. It can be defined like that. Okay, we are defining a Coreset for a particular user. Okay, mapping is non-interleaved, it will come later, but I have mentioned it here. I will explain what this interleaved and non-interleaved mappings are. Okay, but hang on, so this aspect I will explain later, but I have to define it. Okay. Now you see this UE search space consists of 3 Coreset, 1, 2 and 3. Correct? So that's how we are defining it, that for this particular UE, this is your search space. Okay, right? And it is defined at aggregation level 4. Okay, so UE will only search at an aggregation level of 4. That's what this particular UE has been told. Okay, right? And UE will be indicated about the search space. So UE will know that this is your search space. How is it told? We'll talk about it later. But as of now, we assume that UE knows this search space. Fine. Okay. And UE blindly monitors its search space. What does that mean? UE doesn't know where its data is going to come in these Coresets. Correct? Okay. Understood? So what happens? Base station will generate the PDCCH. Just an example. Okay. So K is, let's say A is 140 bits. K will become 140 plus 24 bit is CRC. E, right? Okay, what will be the size of G over here? Okay, each CCE can transmit these many bits, 108, and aggregation level of 4. Okay, so you can transmit 432 bits. Okay, there C is 1, so E becomes equal to G, right? Okay, so polar encoder, how many bits it will generate? We calculated it yesterday. Correct? It will generate 512 bits, right? We saw that. And then the rate matcher will reduce it to 432. Correct? Okay. And those 432 bits will become how many symbols? 216 symbols. Okay. And they can be mapped on to aggregation level 4. That's how G is, right? Okay. So what are we saying here? This is this user's DCI. PDCCH chain has done its processing. Okay. It has generated those many QAM symbols. And what is now is base station decision where to map it. Okay, it will map on either here, here or here. UE doesn't know, that's the blind part. UE knows only about its search space, correct? Okay, that's what has been indicated to this user. Okay, and what base station decides it, that it will map this PDCCH for this user here. Okay, correct? Fine. User gets this slot and it generates, and what it does is it will get this create this 2-dimensional OFDM frame, okay, or OFDM slot. What will happen after that? Okay, so UE will blindly search over its search space consisting of 3 Coresets within aggregation level 4. So this is first Coreset, this is second Coreset, and this is third Coreset. So it will start from this. It will search, okay, right? It will run its PDCCH receiver chain. What will happen? It will fail, right? Because the data is not mapped here. We know how PDCCH receiver chain will work. We have understood that. Correct? Okay, right? It will fail here because this is not its data. It will fail here, it will not, because its data is not defined here. Here it will pass. So how many attempts it will need? It will need 3 attempts. Right? So is the idea of blind decoding becoming clear? What is happening? Okay. This search space has been defined at a particular aggregation level. Okay, right? And it knows that its search space is defined only at aggregation level 4. Okay, right? So this is 1 CC. By the way, like DCI can come at aggregation level 1 also. We'll take another example. Okay, I'm taking a simpler example wherein job of UE has been made easier, or UE is in a poor SINR condition, because that's why these many bits are allocated, right? Okay, base station knows that. Okay, so in this example it is becoming, so one of these Coresets will be used. User doesn't know that which Coreset. User will have to blindly decode, and it finds out in third attempt that there is the DCI which is meant for that user. It decodes the DCI and does it processing after that, and it lives happily ever after. It does PDCCH, PDCCH processing after that. Fine? Okay, so that's the blind decoding part. Let's take another example. Okay, what happens here? Here aggregation level are defined as 1, 2 and 4. Same example, okay, same Coreset allocation, right? So why 1, 2 and 4, why 4 here? This fellow, this user is, let's say, is continuously moving. Base station knows that. Sometime it is hitting good SINR condition, sometime it is hitting bad SINR condition, right? Okay. Now if it is in a poor SINR condition, base station will use aggregation level 4. If it enters a good SINR condition, it will use aggregation level 1. Okay, right? User knows only this, and user knows that this is the Coreset defined at different aggregation levels. Okay, that is the difference now. If it is so aggregation level 1, okay, what are the options? This is aggregation level 1. Its data can come here. Its data can come here. Its data can come here. Its data can come here also. At aggregation level 1, data can come, and the DCI can come. Similarly here, right? Okay, correct. So same allocation. If it is aggregation level 2, what will happen? Data can come in this, data can come in this. Data aggregation level 2, it can come in this, it can come in this. Okay, why can't it come? And so you can say that, okay, can aggregation level 2 begin from here? Because that's also aggregation level 2, right? Okay, correct. This is aggregation level 2. This is also aggregation level 2. I'll show you later that there are certain restrictions imposed on this Coreset. So aggregation level 2 can begin only at even location. 0, it'll go here, and then it'll go here. Right? Aggregation level 1 can begin at any CCE location, but at aggregation level 2, it will begin only at this location or this location. If it is aggregation level 4, it begins only at this location in this Coreset. It doesn't begin from here, it doesn't begin from here. Right? You did not ask me this question, but that's how the Coresets are defined. We'll discuss this aspect later, okay, where it can begin. Fine, okay. So OFDM symbols which are allocated are 0, 4 and 8. In this case, same. OFDM symbol duration 1, period is 1 slot, non-interleaved mapping, okay. So here I am taking two different examples. So UE1 and UE2 search space consist of same Coreset which they will be indicated. I am taking two different UEs. Okay. So what am I saying here? That UE2 search space is also like this. Same search space. It can be defined like that. Okay. So what happens? PDCCH generation, UE1, what will happen? It will have, for this UE1, aggregation it is being sent at aggregation level 4. Same 432 bits. Okay. UE1 is transmitted on symbol 8 as usual. Okay. UE2 is, where is it? What is the aggregation level for this UE2? It is aggregation level 1. Correct? Okay. So for UE2, only these many bits will be transmitted. Okay. And UE2 is transmitted on symbol 4, last CCE. Here. Fine? Okay. So these UEs are blindly going to monitor their search space. What will happen? Okay. UE1 CRC will be validated at 21st attempt. How will it be validated at 21st attempt? See, it is not validated at 3rd attempt. Okay, now it's getting validated at 21st attempt. Why? Because aggregation levels are defined at 1, 2 and 4. What is it going to do? It's going to check at first at aggregation level 1. Right? How many attempts it will make here? 4 attempts. 1, 2, 3, 4. Into 3. 12. 12 attempts, failure. Correct? Then how many attempts here? At aggregation level 2. 2 attempts. 2 into 3, 6. 18 attempts, failure. 19th, 20th, 21st attempt. That's how it will be. Right? The difference here is that the aggregation levels have become more general. Right? Okay. And it is natural in certain scenarios, because the example I gave you was if the UE is like hitting good SINR condition, why should it be transmitted at aggregation level 4? Right? Okay. Base station does not explicitly indicate that at what aggregation level it is going to transmit for each user. This is user's responsibility to figure out where the DCI is being transmitted. Okay. At what aggregation level. These 3 different aggregation levels are defined, but finally at which aggregation level data is being sent, that is blind decoding, right. See how interesting it is, okay, right. User has only been told about this search space and the aggregation level, okay. Similarly, user 2 CRC, when will this be validated? User 2 is coming here at aggregation level 1. So, user 2 will be able to decode this at how many attempts? 1, 2, 3, 4, 5, 6, 7, 8 attempts. It will be able to decode it. When it will be CRC will get validated at 8th attempt. So, at the 8th attempt, UE2 will figure out its DCI is sitting here. Then it will go ahead and decode its DCI and then read the data and decode it. That is what a 5G phone does all the time, right? Okay. So, this is typically blind decoding, okay, and we understand the blindness part. UE does not even know its DCI is coming or not, it has to explicitly do it every time, okay. Now, you understand the importance of designing a PDCCH chain which has low complexity. This is what keeps happening, right, 21st attempt, and as we said there can be more attempts than this. Right? After 36 attempt, it will give up that its DCI is not there, it is sure that its base station has not transmitted a DCI. Okay, that is how core sets are designed. Fine? Okay. And we are making an assumption that these locations, the core set details are known to the user. User does not even know that, and that is a part of the initial network entry where he will come to know. I will give you a brief about how it is indicated to the user, how this core set definition is indicated to the user. That also I will let you know, okay, fine, but this is the blind decoding part, okay, fine. And what did we miss here? Okay, this is the non-interleaved part and the interleaved part, that is what I need to tell you, but otherwise this is how blind decoding works, fine, okay, right. So, let us talk about this interleaved and non-interleaved mapping, okay. So, what we said was 2 different kind of CCE to REG mapping, okay. What are we saying here? Control channel element to resource element group mapping. Control channel element consists of 6 REGs, and how are they mapped? That is what is interleaved and non-interleaved, okay. Let us see that, okay. Core sets with non-interleaved mapping, basically what is happening here, okay, I will show you that, okay. It typically this kind of mapping is done when UE moves slowly and its MCS is reliable, in the sense that, see, what are we assuming, that UE has already reported its MCS in some form, okay, right, and if user is moving fast, okay, MCS will also keep on changing and it will not be reliable, because sometime it will, like if you are moving in a fast speed vehicle, sometime you will observe good SNR conditions, sometime you will observe bad SNR conditions. So, your MCS is typically not reliable, okay, right, because you report it and you have already moved on to a new place where the signal strength has changed, okay, right. And so, I will tell you what is this non-interleaved and interleaved, but in this kind of mapping is used when this is happening, okay. And interleaved mapping is used when UE moves rapidly and MCS become unreliable, okay, right. Basically, what is non-interleaved? Contiguous REGs are used to map onto CCEs, okay, that is what is non-interleaved, okay. Interleaved is basically you pick one REG from one part of the spectrum and another REG from, let us say, another part of the spectrum. They are widely separated, okay? They are separated with PRBs, okay. What happens? Okay, when this condition is happening, okay, right, since the channel is changing fast, okay, so what will happen here is, because you do not have the reliable MCS, you do not know at what link, what should typically the G be, okay, you will have to make a guess, okay, right, and you can only make a guess, but you make this extra effort wherein this mapping, in this interleaved mapping, you will take one REG from, let us say, from beginning PRB, okay, 0th PRB, one REG from, let us say, 25th PRB, one REG from 50th, another from, let us say, you will do it with an offset, okay. And what happens is that if it's 100 megahertz of band, okay, channel is good in one part of the band, might be bad in another part of the band, okay. So, what are you saying? That even if channel is bad in certain part of the band, there is a probability that channel is good in certain part of the band, okay, right. So, and you do not know the MCS reliably. You take a risk, okay, that in certain part of the band channel is good, certain part of the channel the channel is bad. So you typically pick these PRBs or REGs such that certain REGs observe good channel condition, certain REGs observe bad channel condition, okay, correct, okay. Not all of them will observe bad channel condition, right, okay. So we are trying to possibly avoid that condition wherein you don't have the reliable MCS, okay. What you try to ensure is pick these REGs such that at least some of them observe good channel condition, okay, so that the user is able to decode its DCI, okay. If all of them observe bad channel condition, UE will not be able to decode its DCI, and it's a bad thing to happen because control channel UE is not able to decode, okay. On the other hand, if UE is moving slowly, its MCS is reliable, you know which channel is, which part of the band is essentially good for this user, so you map it directly over there, right. So basically this is diversity because you are like picking up such that if one part of the channel is bad, one part of the spectrum is bad, other part of the spectrum is actually at least better than the bad, okay, right. So that way you are mitigating the risk, okay. That's why it is interleaved mapping in this case and non-interleaved mapping in other case, okay. So that's what it is, okay. So you see this mapping. So what is this, okay, this again Coreset we have shown you, this is one symbol Coreset, this is two symbol Coreset, okay. So what is this? This is non-interleaved mapping, that's what I am showing you. All of them are contiguous, correct. This is also all of them are contiguous, okay. And you look at this REG mapping, what is happening here? Here one REG, second REG, okay. Look at this, then it is coming over here. The same color coding, okay, indicates that it is a part of the same CCE, correct, okay. So this and this are part of the same CCE, this and this are part of the same CCE, similarly this, they are part of the same CCE. So you are actually separating them, right, okay, fine, correct. So that was the interleaved mapping. So you have interleaved them across the band or the bandwidth part, right, and that's the idea we have discussed, why that is happening, okay. And what is here? So mapping, this mapping basically when it uses the idea of REG bundle. And what is this REG bundle? I am introducing this term for the first time, okay. I will explain that, but the idea of interleaved and non-interleaved mapping is clear, okay. What does that mean, okay. And REG bundle means what? The set of REGs for which the device can assume the channel is constant, okay. So in this case REG bundle consists of two REGs. Look at this, I have defined, okay, this REG bundle as a set of two REGs, okay, correct. So that's how the standard defines it, okay. And why? Because then it knows at least over these REGs your channel is constant, right, it is not changing too much, okay. It can use that in its decoding, okay. And the reason why you are doing this, that I have already told you, because the channel, if bundle means channel is at least constant, because they are two contiguous PRBs, right. Over those PRBs channel is at least constant, okay. But it changes across this bundle, this is the second bundle, okay, right. So it changes across bundle, that's an assumption which can be made by the user, and then it can process data accordingly, okay. So just for example, if the channel is constant here, it doesn't have to estimate for all REGs, it estimates in the beginning and then uses it for processing, okay, right. So REG bundle size for non-interleaved mapping. So for non-interleaved mapping, what is the REG bundle size? We did not even define for non-interleaved mapping. We only said REG is basically, so you will take 6 REGs and form one CCE, right. There was no notion of bundle over there, correct, because for non-interleaved mapping, what are we saying? It has a reliable, base station has a reliable MCS, it doesn't care, okay. It knows what needs to be done in the sense that it is basically the channel it has a reliable MCS, okay, right. So it will suitably use the G size and get done with it, okay, right. So here the bundle size for non-interleaved mapping is 6, okay. That's basically what we are saying here is there is no notion of REG bundle, okay. But to make things generic, what are we saying here? REG bundle for non-interleaved size, non-interleaved mapping is 6, okay. But you don't use this bundle idea, okay. REG bundle size for interleaved mapping for 2 symbol core set is basically 2 and 6, okay. What are we saying here? That you look at this, okay, that for 2 symbol core set, what are we saying here? Either it is 2, defined like this, or it is over 6, okay. So what is it saying here? That in this case the channel is assumed to be constant over 6 REGs, okay. Base station has certain information about the channel and it says that it is constant over these particular REGs, that is all, fine, okay. So what it says here is that, see, this is 1 CC, correct, okay, right. 1 CC consists of 6 REGs. Other one can come later if it is interleaved, okay, right. This CC, if at let us say aggregation level 2, okay, this is 1 REG bundle, another REG bundle will come later, you can interleave it, okay, but the minimum granularity is 6, okay. So it consists of, so what is happening here? REG bundle consists, if REG bundle consists of 6 REGs, okay, what do we essentially mean? If it is happening at aggregation level 1, there is no interleaving happening, right. If it is aggregation level 2, what will happen here? 1 REG bundle will come here, it will be interleaved and another one will come here, right, okay. Similarly here, one is coming here and one will come here, that is what we are saying. Because what are we saying here? The REG bundle size is 6 over here, okay. If REG bundle size is 2, what will happen? One is coming here, another one will come after 1, 2, 3 here, this one, correct, okay. And what is a bundle? Over which the user can assume that the channel is constant, okay. But why are we doing this? Because we want to make sure that if the base station does not have the reliable information, it at least interleaves these REGs such that if a user observes bad channel condition here, there is a hope that it will observe good channel condition, because these REGs are separated from these REGs by certain number of PRPs, right, okay. And similarly, REG bundle size for interleaved mapping for 3 symbol core set is basically 3 and 6, okay. Here it is 2 and 6, here it will be minimum, because there will be third symbol, so REG bundle will at least be 3 REGs or 6 REGs, okay, right. So finally what happens, each core set can either have interleaved mapping or non-interleaved mapping, not both of them, okay, right. And just to give you a brief idea about where this interleaved mapping will be used, okay, this basically used when user is just entering the network, okay, and it tries to get the minimum basic information about the network, okay, because at that stage base station does not have any information about the user. Where will MCS information come? But it still needs to send some control information to this user, and in that case it just like mitigates this risk by doing this interleaved mapping, because it does not have any information. We will see that, okay, right. Once it has some certain information and the user is fairly stable, okay, with respect to speed, it is moving at low speed and it's entered the network, then it starts using non-interleaved mapping, because it can do better job, right. If you have precise information about the MCS, more or less, okay, then you can encode accordingly, correct, okay, and that is where you will use non-interleaved mapping, okay. So I will stop here, we will continue discussing this in the next class, okay. Thank you.